Okay, hi. In today's video, we will talk about diffraction. I'm changing up the format a bit to see if I can save myself some time. So we'll see how it goes. So this is the last part of superposition, and we will be specifically looking into the comparison between single slit, double slit, and diffraction gratings. Okay, so it's just like putting it all together kind of thing. So we're going to start off by defining diffraction. So this is the definition of diffraction. All right, so there are two key phrases that you should include when writing or describing this definition. So I'm pretty sure you can see from this diagram, this is what diffraction is. Whenever you have a wave passing through a gap, like this, the energy will spread out. Okay, so I will include in the video description a demonstration of this in the ripple tank, but if you observe water wave long enough, you know that whenever it passes through a gap, it kind of like the energy will spread out. Okay, so the first key phrase that you need to mention is that this is the spreading of wave as it passes a gap, okay, or an edge. Later we'll see some pictures. Okay, second point would be that spreading will show a geometric shadow. Okay, what do we mean by geometric shadow? Again, later lah. So you can see, right, the important thing about this diffraction is that the wavelength has to remain the same. Okay, so there are certain properties that they like to ask you. Okay, so mainly, right, you see before diffraction, my highlight length, lambda 1, will still remain the same here lah, lambda 2. The only difference is that the wave shape will begin to curve. Okay, so but when we say smaller diffraction effect, when there's a wide gap, what I mean by this is if let's say you were to draw a line from the gap like this, I mean making it as horizontal as possible, you will notice that yes, there's some spreading of the wave, but the spreading is just this part lah. Okay, this part is the spreading. This part is the spreading. Okay, not as much as this one, because if you were to repeat the process for this tiny gap, hang on. Repeat the process for this tiny gap, what you'll get is something that is like this, right? So your total spread out area actually changes from this little bit, this little portion, to this entire portion. You can see, right, there's a lot of spreading. So this one is a way larger area compared to the wider gap. So the wider gap shows a smaller diffraction effect. Okay, so this one is sometimes asked in your objectives. Okay, so I'm just going to show you what I mean by that. So the objective can look like this lah. Okay, so these are a few examples. Just going to zoom in a bit so you can see. Here it says that there are plane wave fronts passing through a gap as shown. Which property of the waves will be different at Q compared to P? So we know that the frequency and wavelength has to stay the same. Why? Because there's no change in speed. So there's no change in wavelength. And there's no change in all these properties. Okay. And the second reason why I say this, right, is because when you think about it, you have, and I will list this down later for you. You have three wave phenomena. Okay. So the first one is reflection. Not covered in syllabus because when you were young, we talked a lot about this already. Second one is refraction. Refraction is the only one where there is a change in wavelength or frequency. Okay, generally the speed of the wave is speed of the wave is not, I won't say constant, especially for refraction. Your V will slow in denser medium. Okay, so this is the one where there's a change in wavelength so that there's a change in speed. Okay, whereas the third and final wave phenomena, which is diffraction or the spreading of wave, your wavelength, your speed, this one all constant. Okay, so this three, right, is constant, constant, constant. The only thing not constant is the amplitude. And the reason why the amplitude is not constant is because your energy is spread out across a larger area. So if you spread the energy across a larger area, what that means is that you will have less energy per unit space. Okay, so energy is proportional to amplitude. So this one will be because the wave, you know, this teeny tiny part of the wave, this part here that passes through the gap, is spread out. So because it is spread out, so your energy will decrease. So that's why your amplitude will decrease. Okay, the waves are spread out. If you're wondering why my handwriting is so off, it's because I'm sharing screen, as you can tell. So it looks a bit off, but yeah, it is what it is. Okay, moving on. So since we already know what diffraction is, we kind of like try to explain why it happens. So this is explained by Hodgins Principle. Now, Hodgins Principle, most likely butchering his name, is kind of like not in your syllabus, but I feel that you should at least know about it. If not, then the picture of the wave kind of makes no sense, right? Okay, so Hodgins Principle says that every point on the wavefront acts as a point source, and the wavefront as it develops is tangent to the envelope. So if you zoom in into this kind of pictures, right? Let's say we look at this one. Now this is your edge lah. You can see diffraction still occur across the edge because if I were to draw a straight line like this, you can see there's a wave spreading out in this direction. Okay? So the reason why there's some form of spreading, right, is because if let's say I have a wave, let's say this is a wave, this is the original point, okay? And let's say this is my wave source. I'm just going to randomly choose a point and change the color so it's more obvious. I'm going to choose this point as my wave front. So you know wave travel up in circular patterns, right? So this is actually the corresponding wave profile. Okay, something like this. Okay, and then at the end of the day, the secondary wave profile, or where the next position that the wave will be, is tangent to all these little circles lah. They're very cute. We call them wavelets. Okay, so it's, I guess, tangent to that lah. But yeah, so basically you have row number one sending out little wavelets, and then the second row or the second wave front CD will be tangent to these wavelets. And if you are perceptive, you will notice that now every point on CD will be a new wave profile. So will be a new wave source. So this one, this point here, let's say I take this point, it will create this one, then this point will create this one, and then you get another tangent, then the wave kind of like travels out that way. Okay, so the wave is spread out. So basically what we have here is this point create this this wavelet where my mouse is, and then you have a new wavefront. A point on the wavefront create a new wavelet, you have a new wavefront. A point on the new wavefront create another new wavelet, you have a new wavefront. So all this spreading and creating, right, kind of like allows the energy to transfer, because you can see in this particular diagram, with every transition of wavelets, if you were to draw the tangent, which I'm going to do now, if one were to draw a tangent, you kind of like can get this kind of shape here. But also at the same time, you can see I want to be a tangent across this point as well. So let me try. I draw better if I have a whiteboard or paper, but it is what it is. So yeah, so you kind of like get something like this, which explains why the shape here is curving. Okay, curving and then tangent to this circle. here will curve out, then tangent to this circle. So this is diffraction lah. So it's by Hodgins principle, where I am the wave source, I create a wave. Because I create a wave, I got a new wave front. But every wave front is now their own source. It's like I'm a teacher, I create a knowledge. Now every one of my students, they know their knowledge. So they go and tell more people lah. That's the idea. You share out the energy. But because the energy is being shared or spread out, in this case, you will expect that there is generally a decrease in amplitude because the energy is being spread out. All right. So another thing about diffraction is that diffraction has to occur for interference to occur. Okay, because whenever you see whenever these wavelets they meet at these points, interference will take place one. Okay, so this is the initial wavefront. Each point is the source. Whenever they meet here, they have some form of overlapping. Just like you can see whenever we draw the interference pattern, you will have the wave spreading out for the first source, wave spreading out for the second source, and where they meet, this point here where they meet, you get that bright dark fringes. This pattern a bit cacat lah, and I will explain to you why later, but it's okay lah, it's not the best. Okay, I have nicer interference pictures to show you. Okay, so I'm just gonna zoom out a bit. So we know that the thinner or the smaller the gap, the more the wave will spread. So this is a comparison, okay, with different slit width. Now, if you look at this particular picture, right, you will notice that, hey, when the gap is very big, like the first picture, you can see the wave is not really that spread out, but you do see some form of bright dark, small, tiny one, okay? Just like here, when you notice that the slit width will decrease, and then you can see that the light will be spread out, but the intensity is less. So the last picture is less bright than the first picture because again, same amount of energy spread across a large area, so less energy, less amplitude. Okay, so if we were to actually visualize the single slit diffraction, right, and the double slit diffraction, if we compare, this is kind of like a comparison between them. You will notice that the minimas are shared. There's a common minima like here. Like for example, this is a common minima. Okay, the common minima here. It's not really a line lah. Okay, so this part is another one. But the double slit have more common minimas. You also could be asking, why single slit can have minimum one? Well, you see if let's say I were to look at a single slit, so I'm gonna go back, don't worry. This one. I kind of expect to get this picture. Okay, so if I zoom in, which I'm not going to do, zoom in into this particular gap, there is many particles. Each particle become your wave source. Okay, so last time we simplify it and we tell you, oh, you know double slit ma. So because this is double slit there's one wave source here. Let me label them for you. Because it's double slit, so there's one wave source here. It's going to call this S1, and there's another wave source here, S2. Okay, so whenever S1 and S2 reaches the screen, they will have different wavelength. Different part length. So let's say we touch this minimum, pop, and we touch this minimum, pop. So they are delta L. Hey, remember? Destructive interference. So this delta L at this point, because here is a minimum, you can say that your delta L between your S1 and S2 actually is not lambda over 2, you got 1, you got 2, you got 3, you got 4. So this would be 0.5, 1.5, 2.5, 3.5, 3.5 lambda. Okay, so you can see that we are treating each gap as a single wave source. But if you look at your single slit diffraction, what we'll do is we'll just treat a particle on top here, because the gap here got many particles as a source, and then we treat a particle below here as a source. Ta-da! So you kind of like can actually repeat this, and you notice that because this is a shadow of this, there's some form of envelope here. Okay, so actually if you want to be very accurate, your bright dark fringes, although the gap is about the same, When I say the gap is about the same, I mean the distance between bright and bright and dark and dark. Let's say if I take bright, so the distance between this bright and the middle of this bright. Let's see. I can call this. Okay, the distance between here and here is about the same as maybe the distance between here and here. Okay, it's too small. I can't do this. Okay, so it might be the same between like here and here. Okay, just like the distance between here and here is also the same, and the distance between maximum and maximum middle here is also the same. So all of this is your x lah, okay? And if you remember, your x is lambda d over a, or d is ax, lambda is ax over d. All right, so in this case, right, they are actually very similar, but the difference here is that you don't get the repetitive pattern. So for example, if I were to put them side by side like this, you will get a single slit in this way, and the double slit is this way, but there are some shadow of pattern. Another way to explain this to you is because the wave will spread out more here. So then the intensity will drop. That's why it is less bright when it's further away from the center. Okay, so these are just a few setup that we tend to do in the lab lah. We pass a laser pen through and then you can see the bright dark fringes, but you can see there's an envelope here. Okay, there's a very prominent minima, but we don't concern ourselves with that lah. We just measure the gap between the bright and the bright. All right, so this is not new to you. Okay, it's just proper explanation because this is where they overlap. So the wave will spread out behind each slit like this. Okay, the wave will overlap here, and then you get that bright dark fringes. All right, so just continue. Okay, so if there's one slit, there's two slit, we can do three slit, right? Ta-da! Idea is also here the same. But now you got three slits. So your constructive interference, instead of, in this case, A plus A, you will get A plus A plus A. Wow, 3A. That's why you can see, right, the gap is actually thinner. And then with 5 slit, right, is even thinner. Now this will actually allow you to measure X better, or to know where maxima is better. Because if you look at the double slit, right, where exactly is the center? We just use this agak-agak or roughly lah, right? But actually it is better if we add more slits, because then the maxima become more and more prominent, and the minima, right, the cancelling out becomes more and more prominent. And the reason why we care so much about cancelling out is so that the maximum is more obvious. But the so-called cancelling out actually happen because, look, if I want to cancel with someone, if I am S1 and I need to cancel with S2, our path length have to be just right. 0.5, 0.5, 0.5, right? 0.5 lambda, 1.5 lambda, 2.5 lambda. If I only have one option for S2, it's very hard, It's only at this point can cancel, because it's very hard to find another 0.5. But if I have many options, then the chances of me cancelling is higher. You see here, there's a lot of cancelling happening here because there are many slits. Okay, so like here there's more cancelling. So as more and more cancelling happen, what we're going to do is we're going to generalize to n slit, which is what we call a diffraction grating. Okay, and then your lines will be like super bright. You get that bright spot. And then at certain parts where it's minimum here, you will get nothing. So when you come back to the lab, if you are my student, I will show you in the flash lah how this looks like, but you will get very bright spot because now cancelling is possible. Okay, so if you look at this, imagine right now every this is the diffraction grating, right? So every hole on the grating is a wave source left. So if every hole on the grating is a wave source, so this wave source, these are all circular wave. And because it's circular wave, right, this arrow can be at any angle. This purple arrow can point at any angle. So at certain angles, that is nice, perfect, okay, perfect. You remember this diagram in your interference, we got your delta L is A sine theta. So depending on whether you want constructive or destructive interference, because for constructive interference, delta L will be equal to n lambda or m lambda based on this. Okay, so in other words, right, if I want to find delta L, this A is actually the gap here D. This A is this gap D. Let me highlight for you. Okay, so instead of A sine theta is equal to n lambda, we're going to change this to D sine theta is equal to n lambda. All right, so we have D sine theta is equal to n lambda because if you want constructive lah, if you want destructive, then you will take the 0.5 lambda. So, which when it comes to the 0.5 lambda, I would much prefer if you just stick to the bright fringe because bright is very easy to tell where it exactly is. Okay, so once again, you might be thinking where is the theta? So if you look back in the previous interference lecture, theta can be measured here, okay, depending on where the screen would be here. And theta can also, and theta is also this little tiny angle here. And then I already explained in a very long-winded way why they are both the same. I cannot draw so tiny. OneNote doesn't allow. Okay, so this is my theta, and this is my T. This is also theta to the horizontal. Okay, find the proof in the interference chapter. All right, so basically, right, what you need to know is that whenever there's a diffraction grating, we can generalize to d sine theta is equal to m lambda, and you're like, but means this one is also interference. Like, correct. It's the same equation, guys. But they're very cute one. They don't tell you it's the same thing. There are actually two equations. There's this one, d sine theta is equal to n lambda. So the theta here is measured from the center of the slit to where the bright fringe is. So let's say you want to use m is equal to 1, then your theta will be measured from center to m is equal to 1 here. Okay, this is your theta 1. If you are using m is equal to 2, let's say this one, then again the theta will be measured from the center to theta 2, and this one is your bright fringe. Okay, so there we go. So it's just using this equation, but this equation is not like a new equation. It is something that you have already known because we have used this to derive this. You remember? Okay, so I'm gonna just put it together. But before that, what happens when we pass through a light with one wavelength? So one wavelength, you have a fixed value to sub into this equation, right? Then you will get bright lines, lor. But if you put white light, then you will get many wavelengths. And when you have many wavelengths like this, you kind of like have some rainbow shading, but the center is always white because at the center, all the wave will arrive with the same path difference, which is 0. Remember? So when they arrive at the center, they travel through the same distance. And let's say this is the center here. So all the slit will travel the same distance, 0 lor. So let's say you take this point center here, same distance, same distance, same distance, same distance. Okay, so imagine a bit lah. So because they travel through the same distance, I mean, this is your 0, okay, because the delta L is always 0. So you get a white light here. I'm not sure if blue plus red is white lah. Maybe this will be purple, okay? But the reason why I show you this diagram is because you notice that certain color will spread out less than other colors. And the reason to that is because if you think about your electromagnetic spectrum, red light has a longer wavelength than blue light. Okay, So if the wavelength of red light is equal to larger than the wavelength of blue, and we were to follow the equation d sine theta is equal to n lambda, then what you will get is your theta for red must be bigger than theta for blue, because that law. So due to this, right, what will happen is your blue will spread out less. And you see, when this angle is small, they don't go that far away. Okay, so blue will spread out less and red will spread out more. And then if you can check, right, you will notice that, hey, actually, if I check the rainbow, down this part, this red here coincide with this red here, this blue here coincide with the blue here. Okay, so we tend to use this a lot to study gas properties, especially light that's coming from distant stars. We'll talk about this a little bit more in your A2. All right, and one last thing I want to talk about, which is you say d sine theta is equal to n lambda. Very seldom, but I think there's only one past year question who did this to you. Sometimes they will ask you to find this line, this line. Let me draw. They ask you to find, wow, find this distance, the distance of the second order line. We call these lines lah. Second order line. So let's say this is y. The distance of this line to the center bright fringe. So you see you have theta 2. Okay. Normally to do this question, they will give you they have to give you the distance between the grating and the screen lah. So let's say this is D. Okay, so in case you want to find y, tangent theta 2 is opposite y over side D. Okay, again, we did this in your interference derivation. And then we say, oh, sine theta is equal to tangent theta, and then we equate them, remember? Okay, but you cannot use this because the gap is not the same. So you cannot use this because there's no nx. All right, so you have to use these two separately. Okay, and one last thing, although I'm not pretty sure I don't have to tell you this, to find, because your n doesn't extend to infinity, okay? So this m sometimes, by the way, I sometimes will write the equation as d sine theta is equal to n lambda. Same difference, okay? So to find the maximum order, right? Okay, to find this maximum order, what we need to do is actually come up with the idea that sine theta must be less than 1, at most equal to 1 lah. Okay, and then what we can do is we can just sub 1 inside, or you can just substitute sine theta is 1 or theta is 90 degrees. Okay, then you find the value of m lor, and then you take the nearest integer. Okay, so what I mean by that is I think I will discuss one in the example video. Okay, don't worry about it. Okay, in summary, there are 3 wave phenomena as previously mentioned. There is reflection, which is, you know what reflection is, right? Okay, there is refraction. Reflection is the changing in direction when the wave encounters a reflective barrier. Refraction is the change in wave speed when it travels from one media to another media. And finally, not in your syllabus now, but I just tell you lah, diffraction. But I think maybe they also expect you to know because it's from IG lah. This one is a spreading of wave. As it passes a gap or an edge into a geometric shadow. Okay, and I'll tell you now. I don't want to call it bending of wave. I would prefer to talk about this as the change in wave speed as it passes across the boundary of 2 different media, or two media of two different. The correct term here is optical density. Alright. Okay. Now reflection here is the change in direction. This happens a bit everywhere, one reflection. As long as there's a boundary, there will be some form of reflection. Okay, so single slit look like this. Sometimes they can ask you an objective. Okay, double slit, you will get something like this. If you remember, you actually did a question about loudspeaker regarding this. Equation for this would be x. X is lambda d over a. Okay, so I'm going to label all the distances for you. Here to here is your A. Okay, bright fringe to bright fringe, here to here is your X. Lambda is the wavelength of the wave that is incident. Okay, and then D is the separation between the screen and the slit. Okay, so this is D, dn. All right. Okay, now for diffraction grating, just to, again, not to confuse us, I'm going to use the equation d sine theta equal to m lambda for diffraction grating. Okay, you can use n lambda. Sometimes I use n lambda as well. I'm not very consistent in that regard, but yeah. Sometimes if you want to find the distance between, let's say, here to here, you will use tangent. But that's it. That's the end of the chapter. And of course, please don't forget the conditions for constructive and destructive interference. Okay, so I don't even want to call this interference already. Okay, it is just a form of diffraction. Alright, so that's all the time we have for this video. I am actually recording this live content instead of doing a voiceover. Alright, so that's all. You can find this in your content library, and I will see you in the example video. Bye bye.